Hello, everyone, and welcome to Alchemy webinar series. Thank you for joining us today. I'm Tahireh Nematiaram. I'm a Chancellor's Fellow at the University of Strathclyde in Glasgow, and I will be your host for today's session. Today, our first speaker is Dr. Omer Omar. Omer received his PhD in theoretical chemistry from the University of Liverpool in 2023. He is now the co-founder and CEO of Apollo, a Liverpool spin-out, developing a digital platform to accelerate the discovery of new electronic materials. With that introduction, I'm delighted to hand over to Omer. Omer, please go ahead.
All right, thank you very much. Thank you for having me. Thank you for the introduction. Mine's going to be a fairly short and sweet talk, I hope. I think a much more exciting talk is coming after mine. So yeah, be on the lookout for that. Thanks for that. As Tara said, Hello, where's this going? Okay, yes, I'm the co-founder of Apollo, it's University of Liverpool spin-out, and I'll mention a little bit more of that later. But today, as with most of my talks since my PhD, I want to talk about virtual screening and how AI can be coupled with screening for materials discovery. So first of all, a definition of virtual screening. In our review paper, we define it as a computational investigation of a large set of compounds to assess their suitability for a particular function. So for example, if you're looking for highly emissive blue emitting molecules for OLEDs, you may be looking in large sets to extract hit candidates based on a computational workflow, which is called the virtual screening. It works like a funnel. And we have in the past screened databases such as the Cambridge crystallographic database for 50,000 molecules, the Zinc database for 150,000 molecules. So if you want to deal with a number of molecules in that sort of order of magnitude, especially with the methods that you're interested in. So for example, blue emission requires you to compute excited states. That's probably going to use time-dependent DFT. To be able to compute that many molecules, you need to have a very efficient protocol or an efficient funnel to be able to manage those very large input sets. Something that's specific to our group and our screening studies is that we've chosen molecules that exist. So the CSD zinc, all molecules that exist have been synthesized or are even commercially available. This ensures synthetic accessibility or even commercial access to those molecules, because then you can put your money where your mouth is, buy the materials and verify that you've found materials for the property that you're looking for example, a blue emissive molecule. It also introduces or doesn't introduce bias. You're looking at data sets that aren't necessarily designed for any given application. Well, maybe not electronics applications, potentially drug discovery with zinc and things like that, but there is no bias in the project that you're working on. So you may be finding materials that are totally novel, totally groundbreaking, whereas if you generate your own libraries, then you're kind of reducing the chance for that sort of novel breakthroughs. And a very important aspect of using molecules that exist is the rediscovery aspect. So when you're screening to find materials that are known to exhibit a given phenomenon, so single fission, blue emissive, then it is actually just verifying your protocol as you go along. You're finding molecules that are already known. It verifies that your screening is working. So given the screenings that we have done as part of my PhD and research coordinator position at Liverpool and now at Apollo, we were able to find quite a few materials for a variety of rare phenomena. The first one, and this is the one that I'll go into more detail after this slide, is single fission, and essentially these are molecules that are relevant for solar cell applications. Again, non-fullerene acceptors, these are electron accepting materials relevant for solar cell applications. But then we've gone towards also highly emissive molecules, so those that exhibit something called thermally activated delayed fluorescence. This is just a method to a rare sort of phenomenon that's seen in organic molecules that can make them very highly emissive, which is good for OLED applications. Something that's directly related is something called inverted singlet triplet gaps, something thought to be impossible, but we were able to find some materials nonetheless. Again, a route to very highly emissive molecules for OLED applications. And our most recent one, which is a preprint at the moment, is dual emitters. And this was a joint theory experiment screening where we were able to find materials that are or molecules that are dual emitting. So normally there is something called Cash's rule, which allows makes it so that a molecule only emits from its lowest excited state. However, these are materials that emit from multiple excited states, so important for things like sensing and optical memory. But the example that I want to go through is singlet fission, which is essentially a 2-for-1, buy one, get one free on electrons through the circuit. So you have a photon come in, excites a molecule to its S1 state or a high excited state. And then, well, usually it's the S1 when you're looking at singlet fission because it simplifies the picture a little bit. But then it shares that energy with a neighboring chromophore, an identical molecule, and they both drop to their triplet state. So for this to occur, you can probably guess that the singlet needs to be at least twice that of the triplet for this to be an energetically favorable condition. So unless you're putting energy into the system, then this is a condition that needs to be satisfied. And we screened at the time the crystal structural database for molecules. So as many of you will know, at the time it was 1 million instructions. Most of them are inorganic. We're looking at organic molecules. So we ask the question, are they organic? Only 250,000 are. But most organic molecules are insulating. They're not electronically active. So we asked the question, are they semiconductors? Only 50,000 are. But now we can actually screen these using our time-dependent DFT protocol to calculate those excited states, which I showed in the last slide. From those, we found 200 candidates. Now, that's a good number of candidates, but you can see how rare that is, 200 out of 50,000. And that bottom left one is a pentacene-based one. That is a material that is known to be singlet fission active. So that's that rediscovery aspect. And interesting. And so we didn't impose any specific design principles on this. We didn't generate our own library. So we're not introducing any bias that's not already present in the CSD, let's say. And these are synthetically accessible structures because they have physically been made before and can be made again. So they can be taken to the lab. And one thing that's very interesting is that somebody did exactly that. A group completely external to us. They didn't even cite our paper, so they had no idea how we did it. Afterwards, looked at these molecules called Pechmann dyes, which we were the first to introduce as a singlet fission, or predicted to be singlet fission active. They did their experiments and found that they are singlet fission active. So again, a sort of verification, well, we were the first to discover it, but kind of like the rediscovery. And so when you have built a database and you found your singlet fission, you found your joule emitters, what do you do with the rest of the data? Well, one thing that we did was look into AI. At the time, it was only GPT-3, and we tested how can it predict key properties like the HOMO-LUMO gap, dipole moment, and things like that, which are important for these kind of phenomena. And we found that it was quite resilient to messing around with the identifier. So we only input the 1D chemical identifier, which is called a SMILES, and it sort of shows the molecule in a one-dimensional string. And you can sort of mess with the atoms, you could vary them, you could remove atoms, and it was quite resistant to that, which was good. And it did demonstrate some contextual chemical understanding and not just memorization. So this is a path to sort of screening many more molecules in the future without relying on heavier workflows. But going a step more technical is looking rather sort of LLMs, but more machine learning. And employed a much lower level of theory to calculate our excited states. So there's a theory called Zindo. It's semi-empirical. It's a very low level. It's very old school. And as you can see from that left panel, if you try to compute the excited states and compare it with TDFT, it does not really match at all. It is quite terrible. But if you use machine learning to correct that, you can have a very, very good match. And so this is a method that takes seconds instead of hours. And so you can have TDDFT level accuracy for the cost of a Zindo calculation. So this is something that we're working on actively. You can obviously go beyond the S1, you can go to higher excited states, you can go to triplet states, and potentially even other properties as well. So that was a paper from someone called Adam in our group. But the main thing that we're working on with our database is something called Diadem. It was a part of a European Innovation Council of a grant, which was the University of Liverpool, partnered with two companies, European companies, Nanomatch and MQL. And essentially what we did is we want to give access to the databases that we have built. And where AI comes in is being able to query that database using purely natural language. So instead of looking for S1, T1, querying a database, knowing what you're doing, understanding the nomenclature, you can just simply type that you're looking for a strong blue emitter that is stable in air, or a singlet fission emitter material that is non-toxic, and then it will list from a database of 60 million molecules that are all commercially available, can be purchased. Those molecules with the desired optical properties, along with their analogs, electronic analogs, plus in the future novel library generation options. Because this is not just an access to a database, it is also a computational platform. So excited states are not the be-all end-all for properties. You may want to be calculating the charge mobility, the crystal structure, morphology, ionization potential, many properties that require a 3D treatment in space. And these are all accessible at just the click of a button. You don't need to be a computational expert to use it. I think that's something that's missing from many computational platforms. But now, given that, democratizing that access to experimentalists who are looking for these kind of materials. As mentioned, these are available, so amounts, prices, and lead times can all be listed for direct purchasing, all in the same place, all on the same platform, and then you can have the compound delivered to the lab for immediate testing as well. So if you're someone, and particularly an experimentalist or even a computational chemist who's looking for, this is a non-exhaustive list, but PEED opens for the whole transporting layer in OLEDs, or heavy metal-free photocatalysts for chemical synthesis, so it's sort of beyond electronics a little bit, so advanced organic materials, or highly photostable electron acceptors for photovoltaics. They will be just waiting in a database that has data to sort of suggest them. The next fullerene might be waiting in a database. So this is Apollo. This is what Apollo is working on now. If you're interested in just having a chat, or we are looking for early users, but just having a chat, I'll be leaving my email in the last slide. But please do reach out to me or scan the QR code as well there. So just to summarize, high throughput virtual screening is a very powerful method for materials discovery. You can use databases, especially of existing molecules, which allows for a strong verification, especially through sort of rediscovery and direct experimental testing, and of course, low bias in those databases as well. And crucially, we are inverting the direction of prediction now. You're looking for molecules based directly on the property, rather than the other way around. We're not assuming that you already know the molecule you're working for and you're trying to compute their properties. So specifically for us, our applications have spanned from organic electronics and broad, but specifically solar energy, laser dyes, photocatalysis, OLEDs, phototherapies, and more. And as I mentioned, if you're interested in Apollo, just want to have a chat about it, do reach out to me. But otherwise, thank you for listening, and I'm happy to take any questions.